This is video number 5 on electric charges and fields. Timestamps are given in the description box. You can watch parts of video if you are running short of time. In this video, I'll talk about Gauss Law, application of Gauss Law, how to use Gauss Law to find electric field due to an infinitely long line charge of uniform charge density, and also find electric field due to an infinite plane sheet of uniform surface charge density. I'll discuss 6 conceptual questions, 3 questions from JEE Main PYQs, and 2 questions from JEE Advanced PYQs. Finally, I will summarize this video. According to Gauss law, the electric flux that's coming out of a closed surface is equal to the charge which is present inside divided by permittivity of free space. The total electric flux coming to the closed surface integral E dot dA is Q in by epsilon naught. Integral is over a closed surface and Q is a total charge which is present inside the surface. The chosen surface of integration is an imaginary surface and it is called Gaussian surface. Now let us find electric field with an infinitely long straight wire of uniform charge density. So this is the infinite wire which is extended to infinity on both the sides at the top and at bottom. So you have to find electric field at any general point. We should have an understanding how the electric field will look like. So at any point, the electric field will be in the direction which is radially outward. We can get an understanding of this. Suppose the electric field direction, if it is in this direction, that means that the amount of charge present below this point is more compared to the amount of charge present above, which is not true because it's extended infinity on both the sides. So the electric field cannot be in this direction because this means that the electric amount of charge is present above is more compared to amount of charge which is present below, which is not true. So the electric field is radially outward. And also, if you draw a cylindrical surface whose axis coincides with this line charge, any point on the surface is at the same distance r from this wire. So the magnitude of the electric field at any point on this cylindrical surface will be same, but the directions will be different and will be radially outward. So with this understanding, we can use Gauss law to obtain the electric field. Gaussian surface is a cylindrical surface of length L and its axis coincides with the line charge. The electric field is radially outward with cylindrical symmetry. Cylindrical symmetry means on the cylindrical surface, the magnitude of electric field is same because all the points on the surface are at the same distance r from the wire. Angle between the electric field and the area vector is 0 degree on the curved surface and 90 degrees on top and bottom surface. Area vector, the direction is outward normal. So the direction of the area vector on the curved surface is outward normal, so it's in this direction. So the angle between the electric field vector and the area vector is 0 on the curved surface. On the top surface, the area vector is outward normal, which is radially upwards, and the electric field vector is in the radial direction. So the angle between them is 90 degrees. So with the bottom surface, the electric field direction is radially outward, but the area vector, which is outward normal, is downward direction. So the angle between them is 90 degrees. So the angle between the electric field and the area vector is 0 degree on the curved surface and 90 degree on top and bottom surfaces. Using Gauss law, the integral E dot dA over the closed surface is Q in by epsilon naught, and this integral E dot dA will have contribution only from the curved surface. On the top and bottom surfaces, the E dot dA is 0 because E dot dA is E into dA into cos 90. Cos 90 is 0 at top and bottom surface. So only at the curved surface will have non-zero value of E dot dA. So this integral over the closed surface will become integral over the curved surface only. And on the curved surface, the magnitude of electric field is same at all the points because all points are the same distance r from the wire. So the electric field will come out of the integral sign. This integral will reduce to integral dA, which is the total curved surface area, which is 2 pi r into L. R is the radius of the Gaussian cylinder and L is the length of the Gaussian cylinder. So this integration is trivial integration, and Q is a charge which is present inside the cylinder, which is lambda into L. Lambda is uniform charge density, and L is the length of the cylinder. So the amount of wire which is present inside the cylinder is of length L. So that will contribute to the charge of lambda into L. So from this we get the expression for electric field as lambda divided by 2 pi epsilon naught into R. So the electric field goes as 1 by R. Compare this to a point charge where the electric field goes as 1 by R square. But in the case of infinite long wire of uniform charge density, the electric field goes as 1 by R. Now let us find electric field to a infinite plane sheet of uniform charge density, and let the surface charge density be sigma. So this is the infinite sheet. It's a plane sheet. It's extended to infinity on all the sides. The Gaussian surface chosen here is again a cylinder, and the axis of the cylinder is normal to this surface. Again, we should have an understanding of the electric field. How will it look? So here the electric field will look away from the normal. We are assuming that the charge is positive, that is sigma is positive. We can argue that the electric field cannot be in either direction. If the electric field is in this direction, it means that the amount of charge present on this side is more compared to this side, which is not true because it's infinite sheet. It's infinite on all the sides. So the electric field cannot be in this direction. So the only possibility for the electric field is vertically upwards. Similarly, at the bottom, the electric field is vertically downwards. The electric field cannot be any other direction because that means that the charge is on one side is more compared to the other side, which is not true. So this is the direction of electric field, and the electric field at the same distance from the sheet, the magnitude will be same. So with this understanding, we can use Gauss law to get the electric field. So the Gaussian surface chosen is a cylindrical surface. So this electric field lines will cut through the top and bottom surfaces, but the curved surface will just graze the surface. So the electric field on the curved surface, the angle between the area vector and the electric field vector is 90 degrees, but on top and bottom surface is 0 degrees. So it's opposite to the case of infinite wire. Here the electric field is cutting through the curved surface and grazing the top and bottom surfaces. Here it's opposite. Here it's cutting the top and bottom surfaces and grazing the curved surface. The Gaussian surface is a cylinder whose axis is normal to the surface. The direction of V is normal to the sheet surface. The angle between the electric field vector and the area vector is 90 degrees on the curved surface and 0 on top and bottom surfaces. Using Gauss law, which is the total electric flux coming to the closed surface, this is integral E dot dA is Q by epsilon naught. So this E dot dA is 0 on the curved surface because it's 90 degrees. So only the top and bottom surface will contribute. So this integral over the curved closed surface will reduce to integral over top and bottom surfaces only. And the magnitude of electric field at all points on this top surface and bottom surface is same. So we'll come out the integral sign. So it is the integral of the elemental area dA, which is the total area, which is 2 into A, where A is the area of this top surface, and the bottom surface will contribute to another area, so it's 2 into A, and the charge is present is sigma into A. The surface charge density of the sheet is sigma, so this area is A, so total charge present inside this Gaussian cylinder is sigma into A. So from this you get the electric field as sigma by 2 epsilon naught. The direction is outward normal if sigma is positive. So in vector form, electric field is sigma by 2 epsilon in the n cap. N cap is outward normal. Let's solve this question. Two large sheets of uniform charge distribution are here. One is positively charged, one is negatively charged. So find electric field at points A, B, and C. You can pause and attempt this question. So we already have a result for electric field due to infinite plane sheet. So the electric field due to this positive sheet will be in the outward normal direction, and the magnitude of the electric field is uniform at any distance. So the electric field to the positive sheet at any point in space will look like this. It will be away from the positive sheet, and the electric field with this negative sheet will be towards the sheet. So it will be in this direction. So at point A, the electric field to the positive sheet and negative sheet are in the same direction and of equal magnitude. Both will be sigma by 2 epsilon naught. So it will add to give a total electric field sigma by epsilon naught. So the electric field at point A is sigma by 2 epsilon naught plus sigma by 2 epsilon naught, which is sigma by epsilon naught. Electric field at point B, both the electric field to the positive sheet and negative sheet are in opposite directions and of equal magnitude, so they'll cancel. So the net electric field at point B will be 0, and at point C also the electric field directions are opposite and of equal magnitude, so they'll cancel and give a 0 electric field. This is what happens in a capacitor plate where the distance between the plates is very small, so it's as if the sheet is infinite. So all the electric field lines are within the plates of the capacitor. The electric field outside of the capacitor plate is 0. This is the next question. What is the advantage of using Gauss law? Integral E dot ds equal to Qn by epsilon naught. You can pause and attempt this question. The main advantage of using Gauss law is to avoid integration. For example, while finding electric field to be infinite uniform line charge of charge lambda coulomb per meter, one way of getting the electric field is to use Coulomb's law, but the integration that's involved while using Coulomb's law is a little bit more complicated. But suppose if you use Gauss law, then the integration will become a trivial integration, which we already done. So integral will become the integral dA, which is the total curved surface area, which is 2 pi RL. So this integration becomes trivial if you use Gauss law. So the main advantage of using Gauss law is to avoid complicated integration. This is the next question. Find electric field due to a point charge at origin using Gauss law and show it is Coulomb's law. You can pause and run this question. Point charge is located at the origin. So the Gaussian surface which you choose here is a spherical surface, and the center of the spherical surface coincides with the point charge location. So if you take a small elemental area of ds, the flux that is coming out of this area is E dot ds. The direction of the electric field is radially outward. Electric field from a point charge is radially outward, and we are choosing this spherical surface whose center coincides with the point charge. So it is radially outward, and the area vector is outward normal. So that is in the same direction. So the angle between the electric field vector and the area vector is 0. So E dot ds will become E into ds to the power 0. So it's just E into ds. So total electric flux coming to the spherical surface is integral of this one. And the magnitude of the electric field at any point on this curved surface is same because it's the same distance from this point charge. So the magnitude of the electric field will come out of the integral sign. So the integral will become integral ds, which is the total surface area of this spherical surface, which is 4 pi r square. And the flux, total flux coming out of this closed surface is given by Gauss law as Q by epsilon naught, where Q is the total charge which is present inside the Gaussian surface. So from this you get the expression for electric field as 1 by 4 pi epsilon naught, the charge Q divided by r square. So this is same as the one which is got by Coulomb's law, and using the definition of electric field, which says the electric field is the force on unit positive charge. So in some sense, the information contained in Gauss law and Coulomb's law are equivalent. This is the next question. The electric field components in figure are Ex is alpha x raised to the power half, Ey and Ez are 0, in which alpha is a constant 800 Newton per Coulomb meter raised to the power half. Calculate A, the flux through the cube, B, the charge within the cube. Assume A is 0.1 meter. So this is a cube of side A, and this distance is A. So the left face of the cube is at x equal to A, and the right face is at the point x equal to A. You can pause and attempt this question. So the electric field has got only Ex, Ey and Ez are 0. So that means the electric field has got only I component. Since the electric field has got only I component, it will cut through only the left and right faces. Other faces will just graze it, so the flux through them is 0. The electric field has got only X component, so the electric field is in this direction everywhere. So it will cut only the left face and the right face. Other 4 faces it will just graze the surface, it will not cut through them. So the flux contribution will come only from the left and right face. In other words, for other 4 surfaces, the area vector, which is outward normal, is in this direction. So it's 90 degrees. So E dot dA is 0 for both top, bottom, front and back surfaces. But for left and right faces, the angle between the electric field vector and the area vector is 0. So the flux contribution will come only from the left face and right face. So the flux to the left face is integral E dot dA over the left face, and the value of the electric field is dependent on X, and the value of X for the left face is A. So the electric field over the left face is alpha into A raised to the power half, and area vector and electric field vector in the opposite direction. Electric field vector Ex in the I cap direction and area vector is in the outward normal. So this is the direction of area vector, which is opposite to electric field vector. So E dot dA is E into dA into cos 180, and cos 180 is minus 1. So that's why you have this minus sign here. So alpha into a raised to the power half will come out of the integral sign, and integral d is the full area of the left face, which is a square. Similarly, on the right face, the value of x is 2a, so the electric field is alpha into a raised to the power half, and area is a square, and this cos theta is cos 0, which is plus 1. So total flux coming out of the cube is sum of these two. The other 4 faces, the flux contribution is 0. So this is the total flux that is coming out of the closed surface, root 2 minus 1 alpha into a raised to the power 2.5. Now to find the total charge present inside this cube, we can use Gauss law, which says that the flux that is coming out of the cube is the charge present inside, the total charge present inside of epsilon naught. We know the flux present in the cube, so this into epsilon naught will give the total charge present inside. So this is the expression for the charge which is present inside the cube. This is the next question. The point charge Q is placed at the corner of a cube. What is the electric flux through each face? You can pause and attempt this question. So this is a cube, and in the corner of a cube there is a point charge. So you have to find the electric flux through all the 6 faces of this cube. So surrounding this charge cube, we can place 7 more cubes like this. Like if I have a point in this 2D space, I can put 4 squares surrounding that point charge. But in 3D, we can place 8 cubes surrounding a point charge. So the total flux that is coming out of this point charge, which is q epsilon naught, it will pass equally through all these 8 cubes. So through each cube, the flux that is passing through is 1/8 of the total flux, that is 1/8 of q by epsilon naught. That is the total flux that is coming out of this single cube. And the electric field directions will be radially outward. So on the top surface, the right face, and the behind face, the electric field will graze the surface. It will not cut through them. So the flux through these adjacent faces is 0, but this flux through this opposite faces, the highlighted in pink, green, and this orange one, it will cut through them. And these 3 faces, the opposite faces, are placed symmetrically from this point charge. So flux to any one of these faces should be 1/3 of the flux passing through this cube. So it is 1/3 of 1/8. So it is 1/24 of q by epsilon naught. So that is the flux through any one of these opposite faces, and flux through this adjacent face is 0. This is the next question. The point charge q is placed on the axis at a depth h from the opening of radius r. This is a vessel whose opening is a circular opening of radius r, and there is a point charge which is placed along the axis of symmetry at a depth h. Find electric flux through the surface of the container. This is the surface of the container. So you have to find electric flux through this surface. Again, you have to use Gauss's law. You can pause and attempt this question. So the total flux that is coming out of this point charge is q by epsilon naught. That's by Gauss law. And if you know the amount of flux that is passing through this opening, we can find the flux that is passing through the surface of the container. That will be total flux minus the flux that is passing through this circular opening. So to find the flux through this circular opening, use a standard result. That is flux that is passing through a cone of half angle alpha is q by 2 epsilon naught into 1 minus cos alpha. So using that result, and here the cone, you have to find the half angle. So this is the cone, and this is the half angle of the cone. So this is r, and this is h. So cos alpha is adjacent side, that is h, divided by hypotenuse, that is square root of h square plus r square. So the flux that is passing through the circular opening is q by epsilon naught, 2 pi epsilon naught, 2 epsilon naught into 1 minus cos alpha, which is this one. And the flux through the container is the total flux coming to the point charge, that is q by epsilon naught, minus the flux that is passing through this opening. So if you subtract this one, we'll get this as a flux to the container surface. So we can consider some extreme cases. First one is r is 0. That means that the opening is of 0 sides is closed. So in that case, the flux to the curved surface, this container surface should be the total flux, that is q by epsilon naught. So that we should get from this result we have got here. So in this thing, if you put r equal to 0, this becomes, now will become h. So this will become 1. So it will become q by epsilon naught. Another extreme case is h equal to 0. That means that the point charge is placed here. So in that case, half of the flux will go out and the bottom half of the flux will pass through this container surface. So in that case, the flux that is passing through the container surface will be half of q by epsilon naught. So in this expression, if you put h equal to 0, the second term will vanish. So the flux is q by 2 epsilon naught as expected. This is the next question. This is from JEE Advanced 2015. A infinitely long uniform line charge distribution of charge per unit in lambda lies parallel to y-axis in the yz plane at z equal to root 3 by 2. See figure. If the magnetic flux of electric field through the rectangular surface area ABCD lying in xy plane with its center at the origin is lambda L by n epsilon naught. Epsilon is permitted to a free space, then value of n is. You can pause and run this question. So this is an infinite line charge. So the electric field during this infinite line charge will be in the radial direction. So we can find this flux by choosing a Gaussian surface appropriately. So the Gaussian surface chosen here is a Gaussian cylinder, and the axis of the Gaussian cylinder coincides with this line charge, and the radius of the cylindrical surface is such that it will just touch these points B, C, and also A and D. So the length of this Gaussian cylinder is this length of AB, which is of length L. So consider Gaussian cylinder with axis along the line charge and radius such that the curved surface touches AB and CD. So now the flux that is, or the electric field that is passing through this area ABCD is same as the electric flux that is passing through this part of the cylinder. AC. So this part of the cylinder, let it make some angle. This half angle is alpha. So this curved surface of the cylinder makes an angle 2 alpha. The total flux that is passing through this entire cylinder, if you know that, and from that, the fraction that is passing through this part B to C is 2 alpha divided by 360 into the total flux that is passing through this Gaussian cylinder. So first you have to find this angle alpha. So tan alpha is opposite side. So that is this line, that is A by 2. AD is A. So BC is also A. So half of BC is A by 2. And this vertical distance is root 3 by 2A. So which is 1 by root 3. So from that we get alpha as 30 degrees. So 2 alpha, this angle is 60 degrees. So the amount of flux passing through this BC part is 60 by 360 into the total flux that is coming out due to this out of this Gaussian cylinder, which is Q by epsilon naught by Gauss law. And the amount of charge present inside this Gaussian cylinder is the length of this Gaussian cylinder L into lambda. So lambda into L. So it is 1/6 of this one. So comparing this with the expression given in the question, so it is 1/6 of lambda L by epsilon. So that means that N is 6. So the answer to the question is N equal to 6. So this question requires visualization and choosing the Gaussian surface appropriately. This is the next question from JEE Main 2020. An electric field E equal to 4x I cap minus y square plus 1 j cap Newton per Coulomb passes through the box as shown in figure. The flux of electric field through ABCD and BCGF are marked as phi1 and phi2 respectively. The difference between phi1 minus phi2 is. So ABCD is the top face and BCGF is this right face. So you have to find the flux through these two faces and subtract them. You can pause and attempt this question. So the electric field has got only I component and J component. So on this face, the top face ABCD, the electric field is only grazing the surface. It is not cutting through them. Only the K component of the electric field will cut through this face ABCD. So the electric field is grazing this face ABCD. So the flux that is passing through this ABCD will be 0. So area into the electric field vector perpendicular component, the perpendicular component of the electric field is 0. So the flux to the top face is 0. The flux to the right face, the x component of the electric field will cut this face, not the j component. J component will just graze this surface. So only the x component will contribute to cutting this face, that will contribute to the electric flux. So that is 4x I cap, and the value of x for this right face is 3. So the electric field is 4 into 3, 12, and it's a uniform electric field over this face. So the magnitude of the electric field is 12, and the area of this face is BF is 2, and this GF is also 2. So the area is 4. So 4 into 12 is 48. So 5 1 minus 5 2 is minus 48. So the answer to this question is minus 48. It's an integer type question. This is the next question. In finding electric flux using Gauss law, the formula magnitude of electric field is Q enclosed divided by epsilon naught into A is applicable. In the formula, epsilon naught is permittivity of free space, A is area of the Gaussian surface, and Q enclosed is charge enclosed by the Gaussian surface. The equation can be used in which of the following situation? Option A, only when Gaussian surface is an equipotential surface and magnitude of E is constant on the surface. B, only when E is constant on the surface. C, only when the Gaussian surface is an equipotential surface for any choice of Gaussian surface. You can pause and attempt this question. Equipotential surface means the potential at all points on that surface is 0. That will happen if the electric field is normal to that surface. So according to Gauss law, the total flux that is coming out of closed surface integral E dot dA, which is Q enclosed by epsilon naught. The simplest case will be the angle theta, which is between E and electric field is 0, and also the electric field is uniform over that surface. So in this particular case, E dot dA will become E into dA, and since U is uniform, we will come out of the integral sign, and integral dA will become dA. So in that case, the electric field is given as Q enclosed by epsilon naught A. So theta equal to 0 is it's applicable for equipotential surface. For equipotential surface, the electric field is normal to the Gaussian surface. So for equipotential surface, theta is 0. So option A says when the Gaussian surface is equipotential and magnitude of electric field is constant on the surface. So in that situation, the formula for electric field is Q enclosed by epsilon naught A. So option A is true. Option B, electric field is constant on the surface. When electric field is constant on the surface, the magnitude of the electric field will come to the integral sign, but there will be a cos theta here. So the integral will become integral dA cos theta, which will need not be the total area. So it will be different. It might be different from the total area in general. So option B is not true. Option C, when the Gaussian surface is an equipotential surface. When the Gaussian surface is an equipotential surface, cos theta is cos 0, but inside the integral sign we have E into A or E into dA. So that could be different from E into A. So option C is also not true. Option B is not true because it's only applicable only for the first case. So the correct option for this question is option E. This is the next question. The region between two concentric spheres of radii A and B respectively, see figure, has volume charge density rho A by R, where A is a constant and R is the distance from the center. At the center of spheres is a point charge Q. The value of A such that the electric field in the region between the spheres will be constant S. You can pause and attempt this question. So point charge is at the origin, and there is charge between these two spherical surfaces of radius A and B. So the electric field at point P will come from this due to this point charge, and also due to the charges is present here. Here I am using the standard result that the electric field due to a spherical shell is 0 inside, and for outside points it's as if the charge of the shell is concentrated at the center point. So all the charges is present here can be assumed as made up of concentric spherical shells. So the electric field with the charge due to this region can be assumed due to concentric shells, and for each shell this point is outside. So we can concentrate the charge in this region at the origin and find the electric field as if it's an electric field due to a point charge. But the charge is present in this region. It's as if for this point, it's as if it's the inside of the spherical shells of this region. So the charge here, the electric field contribution to this point will be 0. So the electric field at point R, which is in between these two spherical surfaces, due to this point charge, which is K into Q by R square, where K is 1 by 4 pi epsilon naught, plus K into QR by R square, where QR is this charge, amount of charge present between this inner spherical surface and this point R. So to find QR, you have to integrate the amount of charge is present between this and this R. So that will be integral of 4 pi R square d square, this area of elemental spherical shell, into density. So this has to be integrated from R equal to A to R equal to R. And rho, the expression is A by R. So A is a constant, so 4 pi A will come out. So the integral will become R dr, and integral of R dr is R square by 2, and putting the limits we get this one. So putting this for QR here, we'll get this expression for electric field. So here the R dependence of electric field comes from this first term and this term. So effect of these two should cancel for the electric field to be uniform between the spherical surfaces. So that means that Q by R square should be equal to 2 pi A into A square by R square. From this we get the value of A as Q by 2 pi A square. So correct option is option E. This is the next question. A spherical shell of radius capital R carries a total charge of Q given phi as the flux of electric field through a closed cylindrical surface of height h radius r and with the center same as that of the shell. Here, center of the cylinder is a point on the axis of the cylinder which is equidistant from its top and bottom surfaces. Which of the following options are correct? So it's more than one correct question. You can pause and attempt this question. So this is a spherical shell of radius capital R and charge Q, and there is a cylinder of height h and radius small r, and there are different conditions for r and h. So in option A, it says the height is greater than 2r. So height is greater than the diameter of this spherical shell. So the cylinder will come out vertically, and the radius of the cylindrical surface is less than r, is 3/5 of r. So it will be inside. So the cylindrical surface will come out of this spherical shell vertically. So the flux that is cutting through this cylindrical shell is the amount of flux that is coming out of this part of the cylinder. The top and also the bottom part. And also this part, the flux will come out. Here we are using the standard result. The electric field inside a spherical shell of charge is 0 inside. So the electric field at these points is 0. And also here it is 0. So the electric field will only cut through the part of the cylinder which is coming out of the spherical surface. Now the electric flux that is coming out of this cylinder which is coming out of this spherical surface is same as the electric flux coming out of this part of the shell. That is same as the electric flux coming out of the circular disc of this much radius. So to find the electric flux that is coming out of this cone, so that is same as the electric flux that's coming out of this cone of half angle alpha. So the flux that is coming out of this cone is Q by 2 epsilon naught into 1 minus cos alpha. So we have to find this angle alpha. So cos alpha is adjacent side, which is square root of r square minus r square divided by the hypotenuse is capital R. Opposite side is the radius of the cylinder, and adjacent side is hypotenuse square minus this r square. So this will become square root of 1 minus r by r square, and option E, r by capital R is 3 by 5. So using that we get cos alpha as 4 by 5. So from this we get the flux through this top part is q by 2 epsilon to 1 minus 4 by 5, and same amount of flux will go to the bottom part, so it's into 2. 2 comes because one from the top part which is rotating out, another from the bottom part which is coming out of this spherical shell. So this is the total flux that's coming out of this Gaussian cylinder. So option A is correct. Option B says that H is less than 8r by 5 and R is equal to 3r by 5. So H is less than 2r. So if the Gaussian cylinder size is too small, it will be well within the spherical shell, but at a particular value of h and r, it will just touch this spherical surface. So when it happens, we'll get this the length of the diagonal. So let's find this diagonal for this particular value of h and 2r. So d square is h square plus 2r square. So in option B, they are given h as less than 8 by r, 8r by 5. So let's find what will happen when h is 8r by 5. And h is 8r by 5 and r is given as 3r by 5. So 2r is 6r by 5. So r by 5 is common. So r by 5 square. 8 square plus 6 square is 10 square. So from this we get d as 10 into r by 5, that is 2r. So for this particular value of h and r, the cylinder will just touch this spherical shell. But here in option B, h is less than 8r by 5. So the Gaussian shell will be slightly less than, will be a little bit inside this spherical shell. And electric inside the spherical shell is 0. So the amount of flux that is passing through this cylindrical Gaussian cylinder is 0. So option B says the flux is 0. So it is correct. In option C, h is greater than 2r and the radius of the cylinder is greater than capital R. So h is greater than 2r means the Gaussian cylinder will come out of the spherical shell vertically, and this r, radius of the cylinder, is also greater than this capital R, so it will also come out radially. So in this case, the fold of the spherical shell is within this Gaussian cylinder. So now using Gauss law, the flux that is coming to the Gaussian cylinder is the total charge is present inside, that is Q by epsilon naught. So option C says that the flux is Q by epsilon, so option C is correct. Option D, h is greater than 2r and r is 4r by 5, then the flux is Q by 5 epsilon naught. For h greater than 2r and r 3r by 5, the flux is this one. So for this thing, the radius is a little bit more, so the amount of flux that is coming out will be more than this value. So since option A is true, option D cannot be true because the value of r is different. So the correct options for this question are A, B and C. To summarize, Gauss law states that the total electric flux coming out of a closed surface is integral E dot dA is Q in by epsilon naught, where Q is a total charge which is present inside the surface. Electric field through a infinitely long straight wire of uniform linear charge density, lambda is lambda by 2 pi epsilon naught into r. So the electric field goes as 1 by r. Electric field through an infinite plane sheet of uniform surface charge density sigma is sigma by 2 epsilon naught in n cap. N cap is the outward normal. I also take doubt solving sessions for physics and math subjects of JEE and NEET. So if you're interested, you can contact me. This is my WhatsApp number. Fees is nominal and first class is free. Description box has got links and timestamps. You can watch parts of video that you find interesting.